it's a pleasure for me to present Oleksiy Kapustyan. So he's a professor in the University of Kiev. He's a leading researcher in the Institute for Applied System Analysis. And yes, I have to say that he's an expert in the field of multivalued dynamical system and, of course, on its application to partial and ordinary differential equations and inclusion, which will be the topic of the talk. Okay, and he has a large experience in this field with more than 70 publications in Math.net. So please, I give him the word. So can start, please. Thank you.
Hello, everybody. And first of all, I would like to thank the organizers and personally to my good colleague and friend, Professor Valero, for kind invitation to take part in this seminar. Let's start. And today we are speaking about global attractors theory and applications of this theory to evolutionary systems without uniqueness and to impulsive systems. So this lectures consist of 4 parts. In the first part, I recall some basic notions and constructions from classical theory of global attractors, plus some applications to, for example, to reaction-diffusion equations with smooth nonlinear term. And after that, we will discuss multivalued case, so the case when the solution operator is multivalued and we have additional problems how to deal with this object. And after that, we will see how the abstract multivalued approach works for reaction diffusion equation with non-smooth interaction function. And the final part will be devoted to impulsive dynamical system. This is unusual, in fact, unusual from the classical point of view. Object for investigation, and we will see how the classical theory of global attractor can be adopted for the impulsive case. So let's start with classical theory of global attractors. The general scheme is the following. We have evolution problem 1, autonomous evolution problem 1, with initial data 2. So H is a phase space. And of course, if we consider partial differential equation, that this this phase space is infinite dimensional space. And in the sequel, we assume that this space is some Normed space, Banach space, in fact. So we will assume that H is a Banach space. And for this problem 1, 2, we assume that for every initial data U0 from H, there exists a unique solution, for example, in weak sense, of this problem, and this solution belongs to the space H for every value of t bigger than 0. And then the classical dynamical system V can be constructed with the help of the formula 3. So VTU0 equals U of t, where U is a unique solution of our problem starting from U0. The central object in qualitative theory of dynamical system is omega limit set. Here is omega limit set under rather general assumptions. Even in infinite dimensional case, omega limit set is non-empty, compact, connected, and invariant, and attracts U0. So omega limit set of U0 attracts U0 with the help of this limit equality. So if we want to speak about some object which can describe the global limit behavior of our system, we have two candidates. In fact, the first candidate is a compact invariant set A1, which is called pointwise attractor, and this attractor is an attracting set. So A1 attracts every U0 from H, and A1 is a minimal among all such sets. Here and after function dist means Hausdorff semi-distance. And the second candidate, a compact invariant set A2, is called global attractor if it attracts points from the phase space, but uniformly with respect to bounded initial data, and is a minimal among all such sets. Of course, A2 is wider than A1, and the difference between these two objects we can see on this picture. For example, here is two-dimensional ordinary differential equation system, and here is dissipative system, and this system has three unstable equilibrium, O1, O2, and the origin O. And these eight curves in fact consists of two homoclinic orbits, which described by this equation C equals 0. And so the pointwise attractor consists of these 3 points and these 8 curves, and that's all. But global attractor in fact consists of all points inside these 8 curves. So all these points belongs to global attractor. So global attractor is a larger object than pointwise attractor. So what the reason to consider global attractor instead of pointwise attractor? Because pointwise attractor in fact is just a union of all omega limit sets. So it's quite natural object, but unfortunately pointwise attractor, so the simple union of all omega limit sets, is not connected and is not stable. It's easy to see even in this picture, but we will see it later. And the global attractor, under rather general assumptions, is a connected, stable subset of the phase space. So from the topological point of view, from the point of view of dynamical system, global attractor is more appropriate object for investigation. So this is the precise definition. What does it mean, global attractor? So a compact set A is called global attractor of dynamical system V if A is invariant set and it's uniformly attracting set. It's easy to see that if global attractor exists, then it's unique and it's maximal among all bounded invariant sets and minimal among all closed uniformly attracting sets. Among other questions, I want to underline the following one about global attractor. So the existence and topological properties of global attractor. Of course, this is the main question, the first question. And after that, we should investigate structural properties of global attractor and regularity of global attractor. Regularity means that if we consider the functional phase space, our phase space is infinite dimensional, so it consists of functions. So as a rule, global attractor consists of more regular functions than the phase space. And the final question is about dimensionality of global attractor. So let's briefly discuss all these questions and an abstract setting at least. So the existence theorem. The existence theorem is is the following. Assume that dynamical system V possesses the following properties. Continuity, so this map V with respect to the second variable, with respect to variable u, must be continuous. Dissipativity, so there exists a bounded set B0 called absorbing set. So there exists absorbing set B0 that absorbs all bounded subsets. And asymptotically compactness. Asymptotically compactness means that the limit behavior of our system becomes compact. So for every bounded B, there exists a compact set K, maybe depending on B, such that dist VTBK tends to 0 as T tends to infinity. So the bounded subsets for large time becomes closer to some compact set. And if all these assumptions hold, then the set A equals omega from B0 is a global attractor of our dynamical system. And I want to underline that omega of B0 doesn't equal the union of all omega limit sets of U0 where U0 belongs to B0. This is the wider object. And as I said before, if we introduce the notion of stability, this is a classical stability in Lyapunov sense. What does it mean that the compact invariant set M is stable? And then it turns out that without any additional assumptions, only under assumptions of existence theorem, our global attractor will be connected set. And if this map is continuous with respect to both variables, T and U, then our global attractor is stable. So global attractor is connected and stable subsets of the phase space. And if we want to speak about structure of global attractor, so we should introduce the notion of complete trajectory or orbit. So I said gamma consists of all points U of S, where U is continuous. Sorry, it must be right there. So U is continuous function. And the set gamma consisting of all points U of S, where S belongs to the set of real numbers. So this set gamma is called complete trajectory if the following equality takes place. For all T bigger than 0 and for all S, real S, VTUS equals UT plus S. So something like semi-group property along that trajectory. And the first structural theorem claims that if global attractor exists, then it consists of bounded complete trajectories. In fact, it consists of points which lie on bounded complete trajectories. And the next step is to specify what kind of complete trajectories belongs to global attractor. So let N be a set of all stationary points of dynamical system. So it means that N is a set of stationary solutions, in fact, of our evolutionary problem. And we introduce the unstable set emanating from the set N. This unstable set, W of N, consists of all points Z, such that there exists a complete trajectory gamma through this point Z, such that dist UTN tends to 0 as T tends to minus infinity. So that's why W of N, so this unstable set emanating from N. And after that, we should introduce also the notion of Lyapunov functions. So function phi, defined on some subset X, is called Lyapunov function of dynamical system V on this set X. if f is continuous function. And the second assumption is that the function phi must be non-increasing along every trajectory. And the third assumption is that if phi of z equals phi of v t z, then for some t, for some moment of time t, then z is a stationary point of v. So, and the second structural theorem guarantees that if dynamical system V possesses global attractor A, and there exists a Lyapunov function on the global attractor A, then the global attractor, in fact, equals to unstable set emanating from the set of stationary points. And this case is called gradient case. So it means that our system is a gradient system. And furthermore, if the map V is continuous with respect to both variables and the set N is discrete, then the structure of A is particularly clear. In fact, A consists of stationary points and complete orbit joining these points, and that's all. The final characteristic of global attractor is dimensionality, fractal dimension. Here is a definition. So for compact subset of H, fractal dimension is the upper limit of this ratio, where n, m, epsilon is a minimal number of closed balls of radius epsilon, which cover the set n. The main advantage of this definition of this notion is the following fact. So it's known that if dimension of the set M is finite, then this set is homeomorphic to some subset of Euclidean space Rd with sufficiently large D. In other words, it means that if the fractal dimension of our particular set M is finite, then this set can be described with the help of the finite number of parameters. So this is very important. So this theorem, this abstract theorem, claims that if for our global attractor A, there exists a projector P, finite dimensional projector, such that the following two inequalities take place. The first one, consider the projector of V, and the second one, to consider the I minus projector. So, and this inequality, in fact, requires that the I minus P and V must be contraction mapped. So because delta between 0 and 1. So if these two properties hold, then the fractal dimension of A is finite and can be bounded with by this number. So now let's see how it works in very particular case for reaction-diffusion equation with smooth non-linear function or interaction function f. So let's consider this is the parabolic, our parabolic equation. Omega is a bounded domain, and u of tx is a known function, and non-linear f is assumed to be smooth, so from C1, and satisfy the following sign and growth assumptions. 10. This is the sign and growth assumptions, and additionally assume that derivative of f less or equals than L, this bold L. I wanted to underline this assumption because this assumption guarantees the uniqueness of solution of this problem. As an example, we can consider Chaffee-Infante equation, beta u minus u cubed. All conditions will be satisfied with p equals 4. In this case, so this is the simple example. And if we define a weak solution of this problem, a weak solution is a function from this class L2 0T01 intersect LP 0T LP omega. T capital T is the final moment of time, and U is a weak solution is for every test function V the following equality takes place, where norm, sign of norm, and scalar product without indexes are the norm and scalar product in L2. So it's known, it's easy to prove with the help of Galerkin approximation that for every U0, for every initial function U0 from the phase space H equals L2, and for every moment of time T, there exists a unique solution of our problem with these initial conditions. And so just because of arbitrary choice of capital T, we can speak about global resolvability. So we can say that U is a global solution. So U is defined on the whole interval from 0 to infinity with values in L2. And it can be proved that U is continuous function. So we can define dynamical system V according to this standard rule. So VTU0 equals UT, where U is our solution, starting from U0. And here is a list of properties which can be derived from our equation. So the first one is continuity, how we can prove continuity. Here is a consequence of this inequality. The second one is dissipativity. Here is a priori estimates like that. The third one is asymptotic compactness. And here is the sign of gradient. So this is the norm in the space H01. And H01, as you know, compactly embedded in L2. So here is estimates which guarantees some compact behavior of our system. And regularity, in fact, here is a Lyapunov type function for our system, defined on this space. And on this space, this function is continuous function. So I want to underline the presence of this constant from this assumption L, bolt L. So presence of this constant here, here, and here. So it's important. It's important that this assumption plays an important role in this consideration, in this classical consideration. So after that, this theorem guarantees that our dynamical system V possesses connected stable global attractor A, which is compact in the Sobolev space H2. So it consists of more regular functions, and which is attracting set in with respect to topology in H01. So it attracts all bounded subsets from L2, but in topology of H01. And A is a gradient, has gradient structure, and has finite fractal dimension. So this is this is a complete collection of properties concerning global attractor. And now here is a short list of monographs devoted to the subject. You see many famous families and authors which wrote about this object, like global attractor. So now let's consider multivalued case. What I mean by multivalued case, I mean that the case when the Cauchy problem, so our initial value problem, has more than one solution. And surprisingly, there are many problems naturally appeared in applications, which leads to this difficulty, to this problem, so lack of uniqueness. Maybe we can divide this amount of problems into two classes, into two big classes. So the first class is evolution inclusions. So here's an evolution object with multivalued right-hand path, like evolution variational inequalities, like control problems, like evolution equations, but with discontinuous nonlinear functions. And the second class is evolution equation, but for which uniqueness are not known or fail, like three-dimensional Navier-Stokes systems, or multi-dimensional evolution system, or evolution equations with non-smooth interaction functions. So let's briefly discuss all these cases. So it's just a general view of evolution inclusions in Banach space. Here's some sub-differential map and his multivalued map F. And for example, if we consider evolution variational inequalities like that one, so his inequality in the boundary, and this inequality in the boundary leads to the problem like 18 with appropriate choice of phi. This is the first example. And the second example is the control problems. So if we have control parameters in the right-hand part of our equation, and we consider the union over all these controls, we consider union over all these problems, all these controls, so we obtain multivalued F. And we consider instead of the collection of problems with particular controls, we can consider the whole evolution inclusion. And this third example is the evolution equation, but if F is a discontinuous function. So if F is a discontinuous function, then this leads us to the problem like 18. If we consider the convex hull of at the point of discontinuity, if we consider the convex hull at the point of discontinuity. And what about evolutionary equations without uniqueness? Maybe the most famous example is 3D Navier-Stokes system. The situation with this system is the following. We consider this equation, this system, in fact, this is three-dimensional system with respect to V, three-dimensional vector of velocities, and P is a pressure. And it's known that for every V, 0 from the specially constructed phase space H, there exists at least one globally defined weak solution. But there is no result about uniqueness in this class, and no chance to obtain such result. The next example is multidimensional systems like Lotka-Volterra system with diffusion. For example, in bounded domain, is just a polynomial right-hand path, but it's known that for every initial data U0 from the phase space H, there exists at least one globally defined weak solution, no problem. But uniqueness is proved only for initial data from very small invariant region. Ci are small numbers, in fact. And for example, and the last example is the reaction-diffusion equation with non-smooth interaction function. So if we consider the same reaction-diffusion equation, but with no assumption on the derivative of f, so we assume only that f is continuous function, and impose growth and sign assumptions, then, for example, this function, if you satisfy all these properties, so it's known, it can be proved that for every initial data from the phase space L2, there exists at least one globally defined weak solution. But for some initial data, non-uniqueness is proved, in fact. So we can construct many solutions starting from the same initial data. So it's the case of non-uniqueness, and so the classical approach cannot be applied directly. So what should we do in this multivalued approach? So the general scheme is the following. We have our autonomous evolutionary problem, and define it on the phase space H, and we assume that our problem is globally resolvable, but not necessary uniqueness. So our solution for every initial data solution exists globally, but maybe not unique. And then we can construct, instead of single-valued classical dynamical system, we can construct multi-valued dynamical system, or M-semiflow for short, G. And this G looks like that. So GTU0 consists of all values of ut, where u is a solution of our problem from some class. I want to underline this from some class because this is the one of main problems, the choice of the class of solutions. Because in many cases, we know nothing about all solutions, and we know something only on this or about solutions from some class. For example, constructed with the help of Galerkin approximation. So the main problems in this approach is, first of all, the choice of class of solution. Here, the lack of good a priori estimates. The lack of good a priori estimates means that we have some problems if, for example, in this case, f has no derivatives, so we have only a small number of estimates. And the third problem is the topological properties of the set of solutions of the Cauchy problem. In fact, in this situation, we face with the necessity to involve set-valued analysis. So because this is the set-valued map, multi-valued or set-valued, this is the same, but we need set-valued analysis for the analysis of our problem. And of course, the main problem is an investigation of characteristics of global attraction. So we need to adopt the main notions of classical theory for our multivalued case. And it can be done. It can be done, in fact. So it can be done. And many years ago, not many, but years ago. So this is the definition, the precise definition of multivalued semiflow. So G is a multivalued semiflow if we have this semigroup property in sense of embedding, and if we have equality here, then G is called strict M semiflow. And the compact set theta is said to be global attractor of M semiflow G if theta is semi-invariant, and for every bounded B, GTB, dist GTB theta tends to 0 as t tends to infinity. So theta is a uniformly attracting set. Semi-invariant, uniformly attracting set. Of course, such object, if it exists, is unique and has some properties, topological, but I want to to pay attention on this fact that instead of, if we have about the case of non-uniqueness in this Cauchy problem, so we cannot expect continuous dependence on initial data in classical sense, because instead of one trajectory we have the set of trajectories, but we can use the analogous of continuous dependence, and this analogous is called upper semi-continuity property. So a multivalued map F is called upper semi-continuous if for any neighborhood U of f of x0 there exists delta such that for every x of or delta from x0 f of x is a part of U. This is the multivalued analog of continuity one of the analogs of continuity. And this example, this simple example, shows that upper semi-continuous multivalued map may have no continuous selectors. And it means that multivalued approach is not a simple union of single valued approaches. So multivalued approach requires some special tricks. So the existence theorem, what we can claim about existence of global attractor, and this is the existence theorem. So let's assume that our M semiflow is upper semi-continuous with respect to second variable, dissipative, so there exists an absorbing set B0, and asymptotically compact in the following sense. So for every Tn tends to infinity, every sequence Cn from G Tn B must be pre-compact in H. If this property holds, then the set theta equals omega of B0 is the same situation as in a single valued case. So this set is global attractor of M semiflow G. And moreover, if the semiflow G is strict, then theta is invariant, strictly invariant set. Again, without any additional assumptions, slightly additional assumptions, some additional assumptions, but not very restrictive, we can prove that a global attractor is connected and stable subset of the phase space. So if in any case our global attractor is connected, and if the graph of multivalued semiflow G is compact in some sense, so the following system of limits takes place, then the global attractor is stable, is a stable set. So global attractor, if it exists under other general assumptions, are connected and stable subsets of the phase space. And if we want to speak about structure of global attractor, first of all, we must impose these structural properties on our semiflow G. So let's assume that we have a set K of continuous maps phi, such that for every x of H, there exists at least one phi starting from X. The shift of phi belongs to K for every phi from K, and some analogs of continuity with respect to initial data takes place. In fact, in applications, the set K is generated by the set of solutions of particular problems. So the set K is a set of solutions. And under these assumptions, if we consider multivalued semiflow G according to this formula, then G is in fact a multivalued semiflow. And for such a semiflow, we can speak about structure of global attractor. In fact, we can introduce the notion of complete trajectory through this embedding. And of course, if our assumptions K1 and K2 hold, then any complete trajectory satisfies the classical property characterizing the complete trajectories. So, and the structural theorem guarantees that if we assume that assumptions K1 and K2 and K3 hold and M semiflow possesses a global attractor theta, then theta consists of points lies on a bounded complete trajectories. Let's consider application of this construction to reaction-diffusion equation with non-smooth interaction function. So we assume that F satisfy the sign and growth assumptions, but without any inequalities on derivatives. So this is the definition of weak solutions. So without any changes with single valued case. And it can be proved that for every U0 from the phase space L2, there exists at least one weak solution. This weak solution exists globally and belongs to the space of continuous functions. But uniqueness is not guaranteed. And very interesting fact that without any additional assumptions on F, one can construct an example of equation like that one, which has point of non-uniqueness of Cauchy problem, and these points are in fact stationary solutions of our problem. So these points must belong to global attractor, and we cannot avoid multivalued approach. So what about structure of global attractor? So let K be the set of all weak solutions of our problem. Then K satisfy all required assumptions, K1, K2, K3, and we can construct M semiflow G with the help of this collection of weak solutions, GTU0. And for this M semiflow, the following theorem can be proved. That are only under conditions 27, so only under growth and sign assumptions, without any additional assumptions. Our M semiflow G has an invariant, connected, and stable global attractor theta, and this attractor consists of bounded, complete trajectories. In general case, in fact, gradient structure of theta is an open problem. I don't know if it's true or not true, but in some special cases, the gradient structure was proved. So assume that dimensional of omega less or equal than 3, and the p less or equal than 4. So we can consider cubic nonlinearities here. So if we assume that the dimension of omega less than 3 or equal than 3 and p less or equal than 4, then we can claim that global attractor theta is a compact set in H01. So it consists of more regular functions than the phase space A2. And theta is an uniformly attracting set in topology H01. So it attracts all bounded subsets from L2, but in H01 norm. And finally, theta has gradient structure. So it consists of bounded complete trajectories emanating from the set of stationary solutions. Here is a almost complete collection of properties, which, as we saw, hold in a single valued case. So now we can prove that it also holds for multi-valued case. And except of dimensionality. What about dimensionality? And unfortunately, we cannot expect. The finite dimension cannot be expected in non-smooth case. Why? For example, let's consider a function fk equals minus uq plus sine ku. And k is an arbitrarily large number. But in fact, growth and sign conditions take place for constant which do not depend on k. So we can assume, we can speak about global attractor of reaction-diffusion equation with this function fk, and gk is the corresponding dynamical system. In this case, for every k, fk is a smooth function. So we have single value dynamical system. And if we consider 0 as a stationary solution of our problem, then it turns out that the unstable set emanating from 0, of course, it must belong to our global attractor theta k, but it can be proved that dimension of this unstable manifold equals nk, and this nk tends to infinity as k tends to infinity. So in any case, fractal dimension of our global attractor theta k bigger or equals than nk, and for every k, if we increase the number of k that we obtain, that global attractor global attractor is not finite dimensional. And I want to underline that in this situation, the derivative of fk at point 0 equals k. So derivative at the stationary point is unbounded. This is the reason why we cannot speak about finite dimensionality of global attractor in our non-smooth case. And so let's the final part of this lecture is devoted to impulsive systems. What does it mean, impulsive dynamical system, and what difficulties we face in this case? So impulsive system is an autonomous system like that one, but the phase point may have jumps when this phase point reaches some fixed subset M of the phase space. So in fact, our system consists of evolutionary equation plus the jump law. The jump law is I is a value of this jump. So is a value of changes, of these instant changes, and M is called impulsive set, and I is called impulsive map. So assume that these impulsive trajectories are right continuous. So, and assume that for every u0 from H, there exists a unique, globally defined, right continuous solution of our problem. What the difficulties, what the problem with this system? The first and the main problem is that we have no continuous dependence on initial data in this case. There is no result about continuous dependence on initial data in impulsive dynamical system. So we cannot expect that omega limit set is invariant. So omega limit set in generally is not invariant. So we cannot expect the property of invariance from global attractor. So we cannot define global attractor itself, because the requirement of invariance is a part of definition of global attractor. So this is a problem. The problem of construction of omega, not in construction, but the problem in properties of omega limit set. Omega limit set depends on impulsive parameters M and I. So the classical dynamical system theory cannot be applied in this case. And we need to adopt some results if we want to obtain some limit dynamic in terms of attractors. This is the classical example. This is the classical example on this picture about unusual behavior of dynamical system, impulsive dynamical system. So let's consider two-dimensional ordinary differential equation system. Here is a linear case, linear system which has a focus at the origin. There is a focus, but we have impulsive map M and the set M bar. So, and our trajectory behaves like that. So when the trajectory reaches the set M, then it jumps to a new position, I of u, yes, on the circle M bar along the radius, So they move, and after reaching the set M, they jumps into a new position along the radius. So, and it's interesting that if this number is not rational, then the trajectory, every trajectory is dense in this disk. And in fact, omega limit set of this planar system is a whole disk between sphere of radius R1 and R2. The whole disk is an omega limit set. And other very important, not properties, but difficulties in this case, and that this set, this omega limit set, this disk is not invariant. Because if we start from this point, from the point of M, for example, this one, yes? If we start here, then without any jumps, we will tend to the origin, to the point 0. So our disk is not invariant. But in spite of these difficulties, it's possible to construct impulsive dynamical system, and it was done. So the construction looks like that. We have V, a classical continuous dynamical system generated by our evolution equation, yes? And we have set M, which is our impulsive set, and we have map I, which is our impulsive map. And here's two assumptions, 1 and 2, which allows us to claim that our trajectory does not stick on M, And also we must introduce the function phi of x. This is the moment of time. This is the first moment of time when our trajectory, which starts from the point x, reaches the set M. So this is the first moment of intersection of trajectory of dynamical system V, the set M. So then the construction looks like that. If our trajectory is not impulsive, so it has no jumps, then this our impulsive trajectory V bar coincides with non-impulsive trajectory V. No problem. But if we have impulsive moments and phi of x is the first moment, this is the first jump, then V bar looks like that. V bar Tx equals V Tx if T strictly less than this moment of time, the moment of jumps. And at this moment of time, we write here a new position of our dynamical system. And after that, considering x1 plus as an initial point, we can repeat this construction and finally obtain the following formula. For V bar. V bar is our impulsive dynamical system. Here is we have finite or infinite number of impulsive points and moments and corresponding moments of time, Tm. And if we assume that every V bar is defined is defined globally, so it means that either number of impulsive points are finite or this series is convergent. Okay, so if we assume that V bar is defined globally, then without any problem we can prove that V bar in fact is a semi-flow, is a dynamical system, so the semi-group property holds. But of course we cannot speak about continuity in any sense. And so we need to adopt the notion of global attractor. And we can use here the well-known notion of uniform attractor. So what does it mean, uniform attractor? A compact set is called uniform attractor of our dynamical system V bar if A is uniformly attracting set, and instead of invariance we can require minimality property. So A is a minimal among all closed uniformly attracting sets. Of course, if dynamical system has a classical global attractor A prime, that A equals A prime, no problem. But and for uniform attractor we have a criterion. In fact, dynamical system V bar has uniform attractor if and only if it's asymptotically compact. And this attractor is given by the following formula. So we have some basis to prove the existence of uniform attractor in particular impulsive system. But we face with unexpected problems here. Let's consider the very trivial linear case. Let's consider linear case. Here is a parabolic linear problem, and if we use the Fourier methods, then we have the precise formula of solution. And we see from these estimates, here is lambda 1 from the Poincare inequality. So we see from these estimates that this problem has global attractor. This global attractor is 1 point, 0 point, and this 0 point in exponentially attracting point. So the ideal situation in this case. But if we introduce the impulsive set M like a sphere of radius epsilon for sufficiently small epsilon, and it introduce the impulsive map I, just a multiplier of 1 plus mu is the simplest variant of impulsive map. So then we can prove that for every epsilon and mu, for sufficiently small epsilon and mu, this problem with these simple impulsive parameters generates impulsive dynamical system V bar without any problem. All assumptions are satisfied, and this system will be dissipative. But this system doesn't possess uniform attractor. So this is an example when uniform attractor doesn't exist. Why? Just because too many impulsive points on this sphere. Too many impulsive points. So the sphere is not a good candidate for impulsive set, And instead of sphere, we can consider hyperplane like that one. So this is the set M. Here's a Fourier coefficients, and we fix the first P Fourier coefficients and construct hyperplane with the help of these coefficients. Hyperplane, sum I from 1 to P, alpha I, Ci equals A. Here's our impulsive map, our impulsive set, and M prime is a set of images, and our impulsive map I acts from M to M prime, and this impulsive map I change only these first P coordinates. Oh, just an example. For example, the simplest example is when I just an increase, an increase in 1 plus mu times the first P coordinates. Here is a one-dimensional example. This is the very simple example when only first coordinate undergoes impulsive effects. Only first coordinate. So the impulsive set M is the scalar product Y C1 equals A, and the impulsive map I increase this coordinate in 1 plus mu times. That's all. This is the simple case. Here is a two-dimensional case, one variant, and here is two-dimensional case, other variant, how it can be. It's, I think, it's many invariants, many variants how the impulsive map I can be act. But in general case, I can prove that just a moment, this evolution problem with these impulsive parameters generates impulsive dynamical system V bar, which has uniform attractor, and this attractor can be calculated. In fact, for this attractor, the precise formula can be found. Of course, this is the simple, not simple, but just a calculation, because we have a precise formula for solution. So no problem to calculate how this solution behave as t tends to infinity. But from this formula, we can see that this attractor A is not invariant. And the second very important step is that this formula preserves under small perturbations of our right part of differential equation. So in fact, the following result takes place. If we consider weakly nonlinear problem, case epsilon is a small parameter, but f is nonlinear function, continuous and bounded, but nonlinear function. And if M and I are the same impulsive parameters, so M is a hyperplane and I acts only on the first P coordinates, then for sufficiently small epsilon, it can be proved that this problem generates impulsive dynamical system V epsilon bar, and this system has uniform attractor A epsilon, and this attractor tends to this guy as epsilon tends to 0. And so a few words about invariance. So as we saw, our uniform attractor is not invariant, in fact. For example, let's consider this this linear problem with impulsive parameter which touch upon only the first coordinates. And so this is a global attractor in linear case. And from this formula, we can see that in any, it's, I mean, this, here's one. So this example, So we have our parabolic problem plus impulsive parameters, and here is our global attractor A, not global but uniform attractor A, and it's easy to see that A is not invariant in any case. So A is not negatively invariant, A is not positively invariant. The reason is that this attractor has a non-empty intersection with the impulsive map M. And the expected, and we can expect his expected result is a hypothesis, something like that, that if we consider A without M, so our uniform attractor, but without impulsive map, then A without M will be invariant. And in fact, this is true. This is true for many situations. Like that one, for example, he's one of the possible theorems devoted to this subject, how to prove invariance of A without M. But you see that these theorems involves this function S. And this function S is a function which describes the first moment of jump of trajectory starting from X. So this is a rather abstract object, and it's in applications, in real applications, it's rather difficult to analyze this function. But for this particular case, it's possible, and it can be proved that for sufficiently small epsilon, this reaction-diffusion equation with impulsive parameters M and I, only requirement is that this impulsive map should be continuous. So this is the only one additional requirement, and for these conditions, we can claim that our uniform attractor A epsilon has an invariant non-impulsive part. So this guy is a candidate for classical global attractor for this problem.
Okay, thank you, Oleksiy, for the nice lecture. Okay, I have a question about the impulsive systems, because of course, in this case, the situation is much more complicated. Even invariance is not true in general, but only with this set, no, without M. But what about the structure of the attractor? Is it possible to say something, or are there any results in this direction, or this is very difficult?
You know, the group of scientists, just a moment, Bonotto, Professor Bonotto, and others from Brazil, they, in fact, they had some results about structure of attractor, but to prove this result, they need to impose very, very restricted assumptions on system itself. So the matter is how to analyze this function S of X. So the first moment of intersection. This is the key moment, how to analyze this function. If we impose some good assumptions on this function, we can construct the classical theory. But these assumptions can fail in many situations. So, but such results exist
Okay.
about structure of global attractor in impulsive case.
Okay, thank you.
Thank you for your attention, colleagues.
Thank you very much. Goodbye.
Thank you. Bye bye.